Hello and welcome to the final video for the GCSE Physics AQA course on space, the expanding universe and the Big Bang. Before we discuss the expanding universe, we first need to discuss the phenomenon known as the Doppler effect. Now the Doppler effect applies to all wave sources. Now to represent a wave source in this video, I've represented it as a little blue dot, and the white lines that you can see emanating from it represent the peaks of the waves as they leave from that single source point. Now a stationary observer will observe the same wavelength no matter where you observe it from, if you're stationary in relation to that spot in the first place. So the green lines, the green arrows on here represent the fact that no matter where you observe from, the wavelength will be the same. If the source is moving, in this case from left to right, the waves that are produced from it will emanate out from the source as it moves. And if the source is moving towards you, then it can appear as if the wavelength has got shorter, represented by the blue line here. And if it's moving away from you relative to you as the observer, then those waves will appear to be further apart, and therefore the wavelength will appear to be longer. Now this can happen with light. The same phenomenon can happen with light if the object is moving fast enough. Normally, this Doppler effect is observed with things like sound waves, is the phenomenon you get when you hear a car or a siren on a vehicle driving past you at high speed. In terms of light, however, we have to think about how we know this has occurred. Because these observations are being made of galaxies that are massive distances away from us. Normally, hot objects give out a continuous spectrum as per the blackbody radiation discussion from the waves topic. However, on analysis, there are dark bands. Now, I've exaggerated the fact in this video just to make the point about what I'm talking about here, but what we effectively observe is sets of emission spectra or absorption spectra where there are distinct dark lines. Now, those dark lines are distinctive to specific elements, and that pattern is fixed depending on the elements that are involved. When an object is moving towards us, we get blue shift, and we call it blue shift because all of the wavelengths, all of the pattern, have shifted towards the blue end of the spectrum, or the shorter wavelength end of the spectrum. If the object is moving away from us, however, we get red shift, and therefore all the wavelengths, same pattern, but all the wavelengths are longer, therefore we call it the redshift. When we look at the universe, when we look at the galaxies, 99.999999999 odd % of the galaxies are redshifted. Something like 100 out of the hundreds of billions that have been observed are redshifted. And on more careful observation, the further away the galaxy is from us, the more redshifted the light from that galaxy appears. So the further away the object, the faster it's moving away from us. This implies that the universe is expanding, a lot like the surface of a balloon is expanding, can be seen to expand. The galaxies themselves stay the same shape, but the distance between them increase, and the further away the point is from where you start, the faster it seems to be moving away from you. This leads us to a conclusion and leads us towards making a theory that if the universe is expanding, well, where's it expanding from? So the Big Bang Theory is our current best explanation for the start or the very early stages of the universe, and it's got two key details to it that you need to know. You need to remember that all of the matter of the universe, or the mass of the universe, was initially in one single small point, which we call a singularity, and this singularity was incredibly hot and incredibly dense, and it has expanded out from that. We don't know what caused it to expand from there, but it does expand out from this single point and leads to the observations of the universe that we currently can make. It's only a theory though. Now, a key bit of how science works that you need to be aware of linked to this and can be brought into a number of exam style questions on this is the fact that it is a theory, because as scientists delve deeper into the information that we can discern from the universe, more evidence comes to light. And this evidence needs to be checked to see if it fits within our current accepted theory. If it doesn't fit in, we need a new theory. or the theory needs adapting so that it can explain any new phenomena that are observed. Now, particularly with the Big Bang, there's a couple of key points on that. Current observations seem to be implying that the universe is expanding at a faster rate. Now, the Big Bang theory does not explain that in any way, shape, or form. So there's got to be some other possible additions to the theory or developments of the theory to get to the point where we do explain it. And one of those things that has been postulated, and subsequently some evidence has been found for, is the concept of dark matter, a substance which has mass, standard mass, which causes gravitational fields, but does not necessarily emit any electromagnetic radiation of its own. This is pretty much where the space topic finishes. There's a lot of other detail that you can look into here regarding what the Big Bang theory is and other pieces of evidence for it, one of which is the idea of cosmic microwave background radiation. I'd advise that alongside watching this, you maybe have a look up and have a bit of an investigation into that piece of evidence for it, because that also links in to the ideas about ideas and evidence, and here's another piece of evidence for the Big Bang as opposed to another piece of evidence that contradicts it.